be two possible hypotheses. One is that the Earth is moving, so Earth is rotating from like west to east. So that's why we see the sun rising in the east and setting in the west. That's one possible option. The other possible option was Earth is at the center of the universe, and then everything is going around it. Sun is going around the Earth as well, and that's why we are seeing the sun rising in the east and setting in the west. So we have two possible hypotheses. What is true? So we experiment. So this is the question. This is what theorists do. And then the experimentalists or the observers in astronomy, they compile data. So over a few like millennia, we all know the story. The Ptolemy had this geocentric model, and then we have the Copernicus who said that sun is the center, and so on. And then we analyze the results, and if the and then we decide whether the hypothesis is true or not. And if it's wrong, we modify that theory, and so on. And this is how research progresses. And finally, we get the results and we explain the phenomena that we are trying to answer. But the most important thing that I think to learn, and that is what we learned during PhD, is to actually ask questions that are answerable. You can ask like a multitude of questions. You can ask like how the universe formed, how are we here, and everything. But those are like important questions, yeah, but those are not answerable questions at the moment. So when I say answerable questions, it means that given the telescopes, or given whatever we have at the moment, what are the things that we can answer? So that's the thing, that's an important thing to learn. Like there are like impossible questions which are impossible now, but they can become possible in the future. So, but we have to like distinguish between what we can answer now and what is to be done later. So research actually does not involve getting like big answers. You don't like make some big discovery out of nowhere. That does not happen. It just depends on asking the right questions and making small progress. And depending on your progress, someone else will make progress. And it's like a combined group effect. It's not an individual thing. Graduate students, undergraduate students, professors, and everyone should come together to do research, and that's how science progresses. Okay, so for the sake of astronomy, how do we do astronomy? So we do astronomy by collecting photons, or what we call as the electromagnetic spectrum. So we want light, we collect light, and then we understand the different phenomena like by studying this light. So it's not always like there are some other cases, but most of the time it's like we can use the electromagnetic spectrum. So the electromagnetic spectrum, as you all have studied in high school, it's made up of different components. It goes from like gamma rays to radio waves. So gamma rays are the highest energy waves. So they have high energy, which means they have high frequency, but they have shorter wavelength. And whereas radio waves have lower energy, they have lower wavelength, they have longer wavelength and lower frequency. And based on which rays, which photons we are using, we study different things in the universe. Let's say if we use like gamma rays to study, gamma rays are produced from high energetic events. So when there is like energetic events, like something is like bursting or something, then we see gamma rays. Or radio wave, and if we see like ultraviolet is still energetic, but not as energetic as gamma rays. So basically ultraviolet rays are emitted when, like, let's say a star is born. A new star produces ultraviolet rays because that's the energy at which we can see the ultraviolet. And then radio waves are like low energy waves. So they originate from like low energy events. Let's say there's like some gas sitting in the gas just sitting in the universe, and we can see them through like radio waves because it's just cold gas. It's not emitting anything. You can see it in radio waves. So that's how we study the universe. We study the universe at different wavelengths, and that is what we call as multi-wavelength astronomy. And another important part of astronomy is that light has a fixed time. Like light has a fixed speed, finite speed. So it takes some fixed amount of time to get from one point to another. So as you can see here, this is like a real time speed of light. So the light takes about 1.2 seconds to come from moon to the Earth. So when we see something, what it means is that the light is being emitted from that object, and it travels that path, and it travels into our eyes, and that's how we see it. So when we see something, it's because of the light that is emitted from that object and it reaches the eye. So whatever we are seeing is when it depends on when the light is getting emitted. So we are seeing moon as it was 1.2 seconds ago. So that means that we are looking into the past. Similarly, sun is about 8.32 light minutes away, which means that light takes about 8.3 minutes to get from the sun to the Earth. So we are seeing 8 minutes into the past. We are seeing the sun as it was 8 minutes into the past. So if suddenly, let's say, the sun disappears, we won't know it immediately. We will know after 8 minutes. So that's what it means. So from Pluto to Earth, light takes about 4 hours. And the nearest star to us, which is the Proxima Centauri system, it takes about 4.25 years for light to get from there to here. So this property of light is very important for us in like piecing together what is happening in the universe. So the farther we look, like the more distance we are looking that much into the past. So as such, we can know how like things are building up as we see further and further into the past. So as I said, we have to ask a question, and the question that we are like the main question that we are trying to answer is the galaxy, like is how the galaxies form and how they evolve. And this is like a pictorial description of that. So before we go into that, but like first of all, what are galaxies? Like, what are galaxies? Can anyone answer that? What are galaxies?
Is this a group of solar systems and
You said group of solar systems?
We can say a
group
galaxy
of
is a huge mass of stars and the interstellar materials which is present.
Yeah, so it's like, so yeah, it's a group of stars, but just a group of stars cannot be called as galaxies, because we have globular clusters, we have star clusters, which are also group of stars. So yeah, so galaxies are individual, like yeah, they are group of stars along with dark matter. They should have both dark matter and galaxy and stars, and they are like individual dynamical objects. That's what we call as galaxies. So yeah, so we want to understand how these galaxies formed and how they evolve. So this is like, this picture shows the typical of how we consider the evolution of universe. We have a big bang, and then there was inflation, when then there was like recombination, when the universe started cooling down, and this whole thing is just the dark ages where everything was cooling down. And then when everything got cooled down, it started like gravity started working, and then first galaxies were formed, and because of the galaxies being formed, there was like a reionization era when everything was ionized. And then finally we have like we have expansion, and we have the present day universe. So this is what theorists have told us, that this is what is happening. But we need experiments, or we need observations to prove that whatever, like what is happening at each epoch, we call this as epoch, like each epoch of time. So we want to understand how the first galaxies formed, how did reionization occur, how do galaxies grow over like different periods of time, and how are they different from present galaxies, and so on. So this is what we are trying to understand. So here I show the Hubble ultra deep field, which was, or the extreme deep field in this case. So this is basically what was taken using the Hubble Space Telescope. So this small box here that you can see, that was the region that was like imaged for like hours at a time, and you can see moon to scale. So compared to this small area, moon is like huge. So zoomed in on this is that same region here. So each point here is a galaxy. You can see that almost everything is a galaxy. I don't think there are any stars here. Yeah, I don't think there's this one single star here. Can you wait? Can you guys see my like cursor?
No, Didi, I think your cursor is
Here?
yes, Didi.
Can you see the cursor now? Yeah. So there's like this one star here, and then there is this one star here. Apart from these two stars, everything else is a galaxy. So you can see that these galaxies have like different properties. The galaxies can have different shapes, different sizes, different colors, and so on, right? So you can see that like some of them are elliptical in shape, some of them are spiral in shape, some of them are red in color, some of them are blue in color, and so on. And you can see that only in this tiny amount of space, you have like so many galaxies. There must be like thousands of galaxies in this tiny space. So there are like a lot of galaxies, billions of galaxies in the universe, and we want to understand how they form and how they are evolving. That's the main question that we are trying to answer. So Hubble, based on the shape of the galaxies, he created a classification scheme that's called as the Hubble's tuning fork. So you can see that initially there are like elliptical galaxies. So you have like, depending on the ellipticity, if it's like round, it's called as a E0 galaxy. But as it becomes more elliptical, it's called E1, E2, and E3, and so on. It goes to E7. And then you have spiral galaxies, which are divided into S normal spiral galaxies, and then SBs. So the normal spiral galaxies, you can see that as it becomes more spiral, it goes from S0 to SC. And then here on the other side, the capital B refers to the bar, which means like you can see that there's like a bar at the center of the galaxy, and then the spirals come from the bar. So these are called as barred spiral galaxies. And again, they can be 0, A, B, C, and so on. Apart from these, there are like some irregular galaxies, which basically doesn't have any shape at all. They're just irregular. So Hubble initially thought that this is like the evolutionary sequence. So galaxies are born as ellipticals and they go on to become spirals. That's what Hubble initially thought. Now we know that is not true. Now we know that spirals form first, and then ellipticals like grow from the spirals. But this is still a useful map to like look into like different galaxies, because spiral galaxies kind of have some similar properties. So it's important to know which classification your galaxy is in order to like study them. But then how do we study these galaxies? We know that they are galaxies, we are collecting the photons, but what are we doing with the collection of photons? So That's where two things come in. One is the photometry and the other is spectroscopy. So here this is like the basic schematic of what happens in a telescope. So we have a primary mirror with a hole in the middle. So this primary mirror is there, and then we have a secondary mirror, which is situated here. So light from the distant star comes and hit the primary mirror. It goes to the secondary mirror, which is again dispersed through a filter or a spectrograph and is saved using CCDs or like detectors. So here, first of all, the primary mirror is what we call as the size of the telescope. So when we say that the telescope is 2.5 meters, it means that the diameter of the primary mirror is 2.5 meters. So some of the largest telescopes that we have now are 8-meter telescopes, which means that this primary mirror is 8 meters in diameter. So you can imagine how large it is. And then here we have a filter or a spectrograph. A filter, it means that you are filtering out only a particular wavelength range of light. So you always measure, like whenever you're doing photometry means basically collecting the photons. So whenever you're doing photometry, you only collect light in small wavelength bands. So that is very important to understand, because we cannot measure the light, entirely, because that will not give us like accurate results. So we need like specific wavelength light. So that's photometry. And then spectroscopy involves basically creating a spectra. So it's like you get the source, you get light from the source, it goes into different like optics, and then it goes into something called as a spectrograph, which basically disperses the light. It's like a prism. So if you know that when you see a prism, when like white light goes into the prism, it's divided into like the rainbow colors. So when the light gets divided into different colors, or basically spectrum means it's like flux as a function of wavelength. So we know the energy that is released at each wavelength, then we get its spectrum. So that's called spectroscopy. And there are two very important things to consider here, which is light collecting area. So if we have a larger primary mirror, we are able to collect like a lot more light. So we have more number of photons. So we can study more faint objects. And then we have resolution. Resolution is the ability for us to like divide two point sources. Let's say there's like some 2 points, two objects are like really close to each other. We can only resolve them, or we can only separate them if their distance is greater than lambda over d, where lambda is the wavelength at which we are observing, and d is the diameter of the primary mirror. So it should be like the distance between two objects. If it's greater than this, then we can resolve those as two separate objects. So these are the two important things that we have to consider when we are doing photometry or spectroscopy. Okay, and then spectra. Does anyone have any question?
Yes, Didi. Actually, Alokendra had a question. So he's asking, what is the minimum height to set up a telescope?
Height? What's that height?
If you can maybe clarify your question a bit more.
Hello, Didi.
Yeah.
I am Alokendra. I have a question that here height means the distance from the ground level, okay, to collect the rays of the stars.
So usually depends on which telescope you're using. So if you can still have like normal, like everyday use telescopes, right? That you can like set up from the ground itself. Like basically you can put it wherever you want and just look at the stars. But since it's a small telescope, the diameter, like as I said, the the diameter is less. So when the diameter is less, theta is like more, right? Since diameter is in the denominator, so theta will be higher. So for smaller telescopes, you won't be able to resolve like individual stars. So so there is no particular height. The height depends on what you want to see and like how much you want to get out of the light pollution. So if you are in the city, then obviously you want to go to like much higher places because there's like a lot of light pollution from all the street lights. So you will get scattered light into the telescope, so you won't be able to see any stars. So you have to go into a height where you cannot like see the, that's why like telescopes, like large telescopes are not built in cities, they're built on mountain tops. So it depends on like what you want to see, yeah. Any other question? Okay.
No, Didi.
Yeah, okay. So let's proceed. So spectra, so as I said, you collect the spectra. When you get the light, you disperse the light and you get like a spectrum. But there are like 3 different kinds of spectrum. If you are like directly measuring the spectrum from the source, as you can see here, if you're like directly measuring it, you will just see the spectrum of the star itself, and it is called as a continuous spectrum because, yeah, the spectrum is just continuous. You will see like flux everywhere. And let's say if the hot gas goes through a like hot light from the hot source goes through a cold gas. So what will happen is that, you know that I think you have all studied like different series, Balmer series and Passion series and so on. So when these atoms, they collect light, they absorb the light and they get excited, right? The electrons get excited from one state to another. So when this happens, you see an absorption spectrum. So basically, the lines that the black lines that you see here, those are the photons that get absorbed by the gas itself. So then you see an absorption spectrum. But if you're measuring the light from the gas itself, so the gas is absorbing the light from the source, but then it gets re-emitted, and then you see an emission spectrum. And in emission spectrum, you only see the lines, only see the emission lines that are there, and the rest of the spectrum will be like blank. So that's an emission spectrum. So using this knowledge, let's look at like the star spectra. So the stars have like different kinds of spectra, and the spectrum depends on the temperature of the stars, like what you are seeing. So as you all know, I hope you all know what's called as like black body radiation. So stars are like perfect examples of black bodies. So just to give like an overview, black body is something that is a perfect emitter, and the only property that it depends on is temperature. And you all know Wien's law as well. So basically, if you are increasing the temperature, the maximum wavelength decreases. So that's what is happening here. You can see that this is like the tail of the Planck spectrum here. So as you can see, the temperature is decreasing from top to bottom. So as you decrease the temperature, the peak here, this is the peak, right? The peak is like shifting towards the right, which means as you are decreasing the temperature, the wavelength is increasing. And when the wavelength is increasing, you go redder. So that's why you see that young stars, which are like super hot, they are blue in color. And while they grow old and they die, they are slowly losing their temperature and they turn red. So young stars are blue and old stars are red. So this is again a spectrum that you can see here. So this O stars are like like newborn stars. They are like high peak temperature stars, and you can see that they're mostly blue in color, and you don't see much of anything in the red. But as you go to the M stars, which are like almost dying stars, they're not technically dying stars, but yeah, I mean, they have like low temperatures, and you can see that they have they are more red in color. And another feature to note here is that when you have like A stars have like strong hydrogen lines here. So you can see there's like H alpha here, H beta here, and so on. And based on these absorption lines that we see, we can detect what kind of elements are there in the star itself. So from this, we see that we have hydrogen lines in almost everything. So we know that hydrogen is present in the star. So based on different like absorption lines in stars, we can know what the star is made of. And then we come to galaxies, but galaxies are not simple. Like stars, for stars, it's like, you just collect the light from the stars, you disperse it, you have like a spectrum, which is kind of like a black body spectrum with absorption light. But galaxies are much complicated than that. Galaxies consist of different stars at different distances, and the stars can have different ages. And then you can also have different generations of stars. Let's say like there was a star which died, and then it created like more metals, and then it released energy when it died. It produced like different elements when it died, and that came together to form the next generation of stars, and so on. So galaxies consist of different ages stars, different generation stars. It also consists of gas. The gas can be cold gas, it can be warm gas, it can be hot gas, depending on where you look in the galaxy. And it also consists of dust. So when you collect spectra or light from the galaxy, it's coming from all these components. So it's very hard to separate the light from stars or gas or dust. Let's say if I collect light in the infrared light can come from old stars, and it can also come from heated dust. So I'm just explaining to you the complications of studying galaxies. So even with all these complications, we try to like understand different properties of galaxies. For example, this here, it shows the same galaxy in different wavelength regimes. So if you see the galaxy in radio wavelength, you can see, as I mentioned earlier, radio waves study cold gas. So here you can see like CO2 molecules here. So basically we know that cold hydrogen lies along these lines in this galaxy. And when we see infrared, it's either cool red stars, or it can also be due to dust. So this specifically here, it's like old stars. So we know where the old stars are in the galaxy here. The optical light gives like optical is usually something that we see, that we can actually see. So those are like middle-aged stars. Those come from middle-aged stars around the age of the sun. So that's how that's what we see here. The ultraviolet stars are, as I mentioned again earlier, that it comes from hot stars, like hot blue stars that are just born. So when we see ultraviolet emission, we know that stars are being formed in that galaxy, and it's like a star forming galaxy. So stars are like being formed, it's not a dead galaxy yet. So most of the spiral galaxies are blue in color, and they emit ultraviolet, which means that most of the spiral galaxies are usually star forming galaxies. And then we have X-rays. X-rays are produced by like hottest regions. So this one here is probably due to a black hole, which I will explain again later. So these are like some of the hottest regions where atoms are ionized, and we can see when we can see that high energy photons. And galaxy spectra is way too complicated. These are like some of the examples. So we have like continuum spectra, which comes from the stars. It comes from the stars, it comes from the gas, it comes from the dust. And then you see absorption lines here. The absorption lines comes from the stars. And you have emission lines that you can see here. The emission lines come from the gas. So each of the lines, each of like the spectra is complicated, yes, but it can also provide like a lot of information about what is happening inside the galaxy. So like based on this, we can know that for sure that there is like something is getting heated, like some gas is getting heated up and it is producing these emission lines. But we have to figure out what is actually heating up the gas, and that's what the research is. Okay, and then we come to Doppler effect. So this is again what complicates the galaxy studies. So you know that I think you have heard of this Doppler effect a lot, but I think the most common example that we use is like, let's say an ambulance is coming towards us. So if an ambulance is coming towards us, you can hear it like higher, right? You can hear the ambulance sound higher if it's coming towards us. But if it's moving away from us, you can hear the ambulance sound fading away. So this is similar to what we see in like galaxies, like in light as well. So if the object is spectra, if the object is stationary, then it just gives you the normal spectrum. But let's say if the object is moving away from us, it's like going away from us, then what happens is that the light gets shifted to longer wavelengths. So you can see here, if like let's say you're looking at this line, if the object is stationary, you can just see it here. But if the object is moving away, this line will get shifted to the redder wavelengths. And this is what we call as redshift. So it's like redshifting. And then, but if the object is moving towards us, the wavelength gets compressed or like it gets shortened. And the line gets shifted to a bluer wavelengths, and that is what we call as blue shift. And this is the effect of like Doppler effect, and this is like one of the things that complicates the matters further. Actually, Edwin Hubble in 1929, he found that what he did was he just started measuring the velocity of like galaxies. At that time, they were not called as galaxies. Actually, at that time, they didn't even know that galaxies are like separate entities. They thought that they were like some nebulae which are part of Milky Way. But anyways, he measured the velocity and distance, and he saw that the more distant you go, the faster the galaxy or the nebula is moving away from us. So he generated this law, which is called as Hubbles Law. V is equal to velocity is equal to h naught d, where d is the distance. So velocity is directly proportional to distance. So the farther away from us it is, the faster it is moving. And it depends on this h naught, which is called as the Hubble constant. It is, there's a joke called it's the most variable constant ever because it keeps changing. Anyway, so that's like the Hubble's law. So we know that everything is like moving away from us. It's like expanding. The universe is expanding. But in 2011, actually this was done like decades earlier, obviously, but in 2011, Nobel Prize was given to these three people, Saul Perlmutter, Schmidt, and Adam Rees, and they found using supernovae that actually the universe is not just expanding, but this expansion is accelerating. It means that like it's not the expansion is not going at a constant rate. It is actually accelerating, and for this they got the Nobel Prize in 2011, and it's exciting. So now we come, so because of this expansion, so there is like two things happening now. There is like, we know that the galaxies are moving away from us, but there are two things happening. Galaxy is actually moving away from us, and then the second thing is that the universe is expanding, so we see that the galaxies are moving away from us. Like, I hope you're getting the difference between the two. So it's like actual motion of the galaxy is actually moving away from us, or it just seems to us like that because the universe is expanding, we see that the galaxy is moving away from us. So that's why we have something called as cosmological redshift. So we can have so we can have the redshift because of two things. We can have we can have a redshift component because the galaxy is moving away from us, and then we can have like a cosmological redshift component because of the expansion of the universe. And this redshift is often used to explain, like, to understand where the galaxy is with respect to us, or where, like, what's the age of the universe at that point. So here in this plot, so like as you can see from the right side, you can see the galaxies, but you cannot, like, just looking at the galaxies, you cannot say how distant they are from us. Like, this can be like a this can be a galaxy that is like closer to us, or it can be farther from us. So we don't know the distance of the galaxy just by looking at it, and without understanding where the galaxy is located, or when the galaxy is located, we cannot actually say anything about it. So that's why we try to calculate the redshift of the galaxy, and this redshift depends on the age of the galaxy, like age of the universe of when we are measuring that galaxy. So here you can see that, like, here in this left side, yeah, I show a plot with redshift as a function of look back time, which means that you're looking back, like it's the, so 0 is now, and then you're looking back in time, you're looking into the past. And on the right side is the age of the universe as a function of redshift. So it's actually showing plots, it's showing lines for different models, like, but I want you to focus only on the green line. So the green line is the most accepted cosmological model. So we can see that at the redshift of 1, the age of the universe was about 7 giga-years, or like 7 billion years. And similarly, at redshift of 1, we can see that it's approximately the same look back time. So you can think, I'm just telling you like an approximate thing, but for redshift Z, the age of the universe is 1 over 1 plus Z of the total age. So 1 over 1 plus Z at redshift of redshift of 1 is half. So redshift of 1 means that at that redshift, the universe was half the age of what it is today, and so on. So for higher redshift, we go into like more farther. So let's say, so redshift of 20 or 24 is about what we consider as like recombination epoch. The reionization occurred at a redshift of 7 or so, and so on. So you don't need to like understand it completely, but just think of redshift as like, start thinking of redshift as like time, like age of the universe. Okay, and then finally we come to like active galaxies. So So what are active galaxies and quasars? So these are like some of the brightest objects in the universe. So originally, when they were seen, we didn't know that they were galaxies. We thought that they are like very bright objects. They looked like stars, but they didn't have the same properties as stars. And then they found that these are actually like galaxies itself, and they basically host, these galaxies host active black holes. I will explain what active black hole means in a minute, but they have like active black holes at their center. And because of the active black hole, they release so much energy that they block out the actual stellar light itself. So they have so much energy. The active galaxies are so bright that you cannot separate the light from the stars itself. So supermassive black holes, now we know that supermassive black holes are can be found in almost every galaxy of like typical stellar mass of Milky Way or higher. So when I say stellar mass, it means that mass in stars. As I said, galaxies is made up of stars, gas, dust, and dark matter. So mass in stars is about 10 power 10 solar masses. So if we have we have supermassive black holes at almost the center of almost all massive galaxies, but they are not all active. I will explain again what active means. And in 2020, like last year's Nobel Prize, it was won by Reinhard Genzel and Andrea Ghez. I would highly recommend you to watch Andrea Gez's videos. She's amazing. She's a great speaker. So if you have time, I would highly recommend for you to listen to her talks on YouTube. So yeah, so they actually discovered the supermassive black hole at the center of our own galaxy, Milky Way. And they spent over 20 years looking for for the supermassive black holes, and for that they won the Nobel Prize last year. Okay, so as I said, the active galaxies have supermassive black holes at their center, and these regions are very compact. And when I say they are active, it means that they are accreting matter. So it is sucking up like gas and dust. The black hole is like sucking up sucking up the dust and gas, or what we call as accretion. It is accreting these things, and that's when you release like a lot of amount of energy. So this whole thing is what we call as active galactic nuclei. So when there is a black hole and it is accreting matter and it is producing energy because of this accretion, it is called as an active galactic nuclei, or AGN. And this area is very small. It's like about 1 light year. So a typical galaxy size is about 100,000 light years. So 1 light year in comparison to that is like very compact. So it's like a very small region in the galaxy, but it is producing so much light that it is like overshadowing the entire galaxy itself. And that's why it is like pretty significant thing. So you can again study the active AGN in using photometry. So you can measure it in radio, you can measure it in infrared, optical, and X-ray, depending on where you are looking at. So this is like a typical diagram of an AGN. So you have like a black hole here, there's an accretion disk, which is basically slowly accreting the material onto the black hole. And then you have like something called as obscuring torus, which is made up of dust. and it blocks out the light from the central black hole. And then you have something called as the narrow line region, and then there is a broad line region. I don't want to go into all these details. It's like its own entire area. And then there is like a jet, which you can see in radio waves. And then you can also study like using spectroscopy. So spectroscopy, galaxy spectra itself is complicated, but then when you add AGN into it, it has like an AGN component. So it becomes much more complicated. But if you see broad lines, so here you can see emission lines here, but you can see that the top one is broad. So that you have broad lines. When you see a broad line, it means that there is an AGN there. But you can also have narrow lines, and you have to like, there are some detection methods which are called as diagnostics, AGN diagnostics, that you use, that you apply on the spectrum to see whether or not it has AGN in it. So let's talk about why it is important, why AGN produces so much light. It's because accretion produces like a lot of energy. So you all know of Pokhran 2, which happened in India. We had like the nuclear tests that took place. So they produced about 10^15 joules of energy. And compared to that, the sun produces about 10^26 joules every second. And supernova, when it's like supernova is when when a star dies, it bursts and it dies, and that produces an energy of about 10^44 joules. But if we have like an accretion, you can see that just a typical like accretion produces 10^40 joules every second. So you can see that it's like a huge amount of energy that is like being produced when an accretion happens onto the black hole. And this is like one of the most energetic processes in the universe. So now that now that we have covered the basics, like, do you have any questions? We can stop here for a moment and like ask any questions, if there are any questions till now. There is no such thing as a silly question. Okay, no questions. Okay, so yeah, so
Hello, Didi.
now, yeah.
I have a question that sometimes we hear that massive particle
Messier
come
catalog.
to hello. Hey, Didi. I mean that as a massive particle which it come towards the Earth. So is it possible to measure by Doppler effect? I mean that you shown.
What particle? What particle? I couldn't hear what particle you said.
I mean basically. I mean, it is not a specific, but
No, are you talking about light or some other particle?
no, I mean some asteroid or anything.
Oh, so asteroid. So as I said, the redshift, the Doppler effect happens on waves. Okay, so the Doppler effect is on the waves. So it's happens on light. You cannot have like redshift for like an object. You will have it because, you know, matter duality. So matter can be like every body is a particle and a wave, but it will be insignificant for the case of like heavy objects.
Okay, Didi.
Yeah. Okay, so let's start with actually talking about galaxy formation evolution now. So now that we have covered the basics, so the theorists have created this model of structure formation, which is called as lambda CDM model. So what it states is that the universe is made up of lambda, which is dark energy, and it is made up of CDM, which is cold dark matter. So this is like the distribution of dark energy and dark matter. So we have about 71% of the energy, 71% of the universe is dark energy, 24% is dark matter, and the rest of the 4% that we actually see are baryons. Like everything that we see are the actual atoms. So we know only 4% of the universe. We don't know what dark matter is. We don't know what dark energy is. We only see its effects. So dark energy is what is producing the accelerated expansion of the universe. So we have seen the evidence of dark energy, but we don't know what it is. We have seen gravitational effects of dark matter, but we don't know what it is. So the theorists say that the universe is made up of cold dark matter and dark energy, and it makes predictions saying that small objects, they merge together to form larger objects. So small galaxies form first, and then they merge together and to form like bigger galaxies. And this is what theory says. And this is like an example that we have seen of merging galaxies. There are like two galaxies here, but they are merging together to form like a bigger galaxy, and we caught them in the process of merging. But yeah, so these small galaxies are what we call as dwarf galaxies. So they are like low mass galaxies which have stellar masses less than the Milky Way. So the Milky Way is like a normal size galaxy. It's like called as a characteristic galaxy because we have like most of the galaxies in the universe, like in present, are Milky Way mass galaxies. So we want to understand like how the Milky Way formed. So we are looking at low mass galaxies. So these low mass galaxies or dwarf galaxies are building blocks of the universe. So we want to understand them, understand how these low mass galaxies form and evolve. So these are examples like these LMC and SMC. Together they are called as Magellanic Clouds. So this is the large Magellanic Cloud, this is the small Magellanic Clouds. You can see it from the southern hemisphere. And these are the closest dwarf galaxies to us. And you can actually like literally see them from like the southern hemisphere. And then you have like ultra faint dwarfs, which are like basically, this is a segue one ultra faint dwarf. Like, can you even see a galaxy here? Like here you can differentiate between like the galaxy and the sky. But here you can see that it's like super faint and you cannot even like separate the stars. In fact, like these are the stars of this galaxy. Like you can see how faint it is. And these are called as ultra faint dwarf galaxies. So that's why it's very hard to study dwarf galaxies, because they're like super faint and we don't know, we don't know whether like those stars that we are randomly seeing on the sky are just group of stars or whether they are like actual galaxies. So they are like faint and it's harder to detect them. So this lambda CDM model, it works on the bigger scales, like Milky Way scales, but it fails to work in this low mass galaxy scale. So we have like some problems with it, which are like, there are three types of problems. One is the missing satellites problem. So when you run simulations of like satellites around Milky Way, like Milky Way has, so what happens is that the galaxies are like rotating around the Milky Way, and then it's supposed to fall into the Milky Way and like basically merge. So when we are comparing the number of satellites that are to be expected versus what we actually see, we see less number of satellites than what is expected. So this is called as the missing satellites problem. And then we have the too big to fail problem, which means that the theory expects, like from theory, we expect like high mass galaxies, like higher mass, but comparatively lower. I mean, they're still dwarf galaxies, but they're big enough to create stars, but we don't see them. So that's why they are called as, it's called too big to fail problem. And then we have cusp core problem, which is shown here. So theory expects, like from theory, we expect this black line, which is basically the density of the galaxy as a function of radius. So from theory, we expect this, a cusp, but from observations, we get this, which is core, so which is called, so we see a difference between the observed density from theory and observations, and that's just what we call as cusp core problem. And this is basically because, so one of the possible solutions which is proposed is that we need energy input to resolve this, which means that the satellites, so to produce galaxies, we need cold gas. To produce stars, we need cold gas, because stars form from like hydrogen. It cools down the hydrogen, and like the gas cools down. And once it cools down to molecular level and then further cools down, then it produces like stars. But let's say there is some event that is happening, which is ingesting the gas with energy. Then it cannot form stars. So it's something is stopping the galaxy from forming stars. And that's why we are not seeing the seeing the satellites. That's like the proposed solution. That's the proposed solution. But then what is producing this energy? It can be either a supernova or it can be an AGN feedback. But supernova alone is like, there have been several studies that have been done, but supernova alone cannot explain these problems. So it is possible that AGN feedback is what is happening in these galaxies, and that's why we are like, that's one of the explanations. But this is what theory states. But we need observations, we need evidence to prove that this is what is happening. And that is what is my research. I am trying to find AGN in low mass galaxies. I'm trying to search for AGN in low mass galaxies so that we can explain all these things. We can explain the issues with lambda CDM model and so on. We can provide like evidence for what is going wrong in these small scales. But it is also important, searching for AGN in low mass galaxies is also important because of some other things, or like some other things that are happening. So the galaxy and the central black holes co-evolve because the galaxy is providing the gas and dust that is fueling the AGN, that is being accreted onto the central black hole. And the black hole is producing energy, which is fed back into the galaxy, which is heating up the galaxy, and it is moderating the star formation that is happening in the galaxy. So it is important to understand how the galaxy and the black hole co-evolve together. So this is my main goal. There are like a lot of things that you can study in low mass galaxies, but I am primarily interested in this part of the science, like how do galaxies and black holes co-evolve. But there are some other aspects of this search. So we know that stellar black holes exist. We know that like when stars die, like massive stars die, they form black holes. They are called as stellar black holes. We also know that supermassive black holes exist, which are at the center of like Milky Way sized or massive galaxies. We know that supermassive black holes exist. But we don't know how stellar black holes go from like low masses to supermassive black holes. So they also, like the proposed solution is that they also merge together to form like supermassive black holes. But then that means that we should be able to see intermediate mass black holes, but we don't have evidence of those. We want to know like whether these exist or not. And AGN in low mass galaxies are prime candidates for this. So if we are able to find AGN in low mass galaxies, we would be able to find intermediate mass black holes. which would be so exciting because you know that LIGO is being planned to be launched in space, which is called as LISA. So LISA is going to be on soon, and LISA will be able to see the intermediate blast black holes, and it will be so exciting to have like candidates for that. And then, as I said, we want to understand how the supermassive black holes grow, and we call the supermassive, like the initial part of supermassive black holes, as seeds. And it's like a whole entire new entire area of astronomy. I'm not going to go into it, but it's like just a very extra point that if we get AGN in low mass galaxies, we will be able to understand the supermassive black hole seed formation mechanism. There are like different mechanisms that can like form the supermassive black hole, and we want to understand those. Not me, but someone else, but like, yeah. That's what is exciting. Okay, so now we have AGN in like, so the previous searches for AGN used SDSS, which is the Sloan Digital Sky Survey. So it's been happening since 2000 to present, it's still happening. It's a 2.5 meter telescope. This is the telescope, and it's basically covering the sky in different wavelengths, and it's observing and it's also taking spectra of different galaxies. So Amy Raines in 2013 did the first like detailed search for AGN in low mass galaxies. So this is like a typical diagram, typical plot or diagnostic that we use for getting for searching for AGN signatures. So as I said, we use like emission line spectra from the galaxies to understand whether or not there is an AGN. So the emission lines are produced when energy is inputted into the gas, and this can be because of star formation or because of AGN. So in typical galaxies, star-forming galaxies are all here, and if we have like AGN, the galaxies reside up here. So basically, it's like the degree of ionization is different between star formation and AGN. AGN produces higher energy photons compared to star formation, so we see like a higher like emission lines compared to star-forming galaxies, and that's how we differentiate between the two. But they found like 136, so they like, I think they looked at over like 36,000 galaxies, and they found only 136 low mass galaxies with AGN signatures. However, further like looking into them, it was like some of them were confirmed candidates, but some others didn't meet requirements in like infrared or radio or something. So it was like not a multi-wavelength approach. So I'm going to use the DESI instrument, which is the dark energy spectroscopic instrument. It just started its survey. It's a 5-year survey of the like over 30% of the sky. And this is, it's so beautiful that it's basically has 5,000 fibers. So it will measure the spectra of 5,000 galaxies at a time. And these are robotic fibers. So each one of this like long thing is a robot. So it's basically, it has 5,000 robots which are working by itself to like set up the fibers. And this instrument will take 5,000 spectra at a single time. So by the end of the survey, we expect over 35 million spectra of galaxies and quasars. And we also have photometry in optical and then infrared. And additionally, when we compare the SDSS and DESI, you can see that like in SDSS, you have like the SDSS targets are shown in white circles. So in this area, you can see that the SDSS has only 2 galaxies. But if we include DESI, you can see that all this, like all these extra sampling of galaxies is taking place because of DESI. So you're observing a lot more galaxies. We are observing a lot more galaxies using DESI compared to SDSS. And we are also going 100 times fainter than the SDSS. So we have a more chance of detecting AGN in low mass galaxies compared to SDSS. But in addition, I'm also concentrating on multi-wavelength approach. So I'm also looking at I'm also looking at X-ray wavelengths and infrared wavelengths and optical wavelengths to like simultaneously find AGN in low mass galaxies. So I cannot show you the actual plots and everything because it's within the collaboration, but I'm showing you this main preliminary result which I just started. So this shows redshift as a function of absolute magnitude in G. Basically, just think of it as like faintness of the galaxy, and the gray ones are the AGN that was detected by Amy Raines in 2013. And the pink and the green points are the galaxies, like AGN galaxies that I discovered. And so we will be extending the galaxy search for AGN to fainter galaxies. And you can see that we are going to farther into the past. We are going to higher redshift. And preliminary search, I just did a preliminary analysis for now, and we have 55 possible candidates. I need to investigate further, but for now we have 55 possible candidates. So what next? So these are some of the questions that I'm trying to answer. I want to know how many dwarf galaxies have AGN, whether they have duty cycle, which means that is there like a phase to that? Like they are active, like the black holes are active at some point and then they stop accreting and then they start accreting again. Is there like something happening in these dwarf galaxies? And how do these AGN, like this energy output, affect the growth of dwarf galaxies? And if there is any environmental significance, if there is anything that is outside of this galaxies that is affecting this AGN. So these are some of the questions that I want to work on in the future. So that's where I stop. Vera Rubin is amazing. So she's one of my role models. I mean, she was one of my role models. And I just wanted to mention her because she was she discovered dark matter, and we are now like constructing a telescope in Chile. It's an 8-meter telescope which is going to survey the entire sky, like southern sky. And it's called as, they named that telescope after her. It is called as Vera Rubin Observatory. And it's the first time in the history of astronomy that a telescope has been named after a woman. So I just wanted to say that. Yeah. Any questions?
Yes, thank you, Didi, for the talk. So there are a couple of questions in the chat box. So I'm going one by one in the order in which they were sent. So first is Animesh's question. He's asking, is there anything opposite of dark matter, like white matter?
No. So we call it dark matter because we just cannot see it. It's not because it's black or anything. It's just called dark matter because we don't see it. Usually, okay, this is like entering into fringe science. Basically, it's like we expect antimatter for everything. So like for electrons, we have positrons. It's an antimatter, like it's an anti-opposite of electrons. So like that, in like fringe science, we expect there should be an anti-dark matter, but we don't have any evidence of that.
Okay, Didi, thank you.
Is exactly I guess the next question is answered because this was Ian asking, is the dark matter that which we don't know? I mean, as we don't know that matter, it is dark dwarf. So yeah,
Yeah.
exactly what.
So
Hmm.
it is called as dark matter because we don't know, and also it does not. Also, it's because it does not participate in any electromagnetic, like it does not interact with us using electromagnetic radiation. It only interacts gravitationally. That's why we see the effect of the dark matter, but we don't know what it is. It does not it does not interact with us using photons.
And so the next question is from Akash. He's asking, is stars or objects are closer in low mass galaxies than that in high mass galaxies?
Uh, no, no. It's like galaxies, like the galaxies are a whole things, right? So galaxies are like the galaxies as a whole are either close to us or they are like farther away from us. So yeah. So like you can have low mass galaxies that are like very, very farther away from us.
No, my question was that the star is inside that of galaxy. Stars are closer or farther in low mass galaxies or that in of high mass galaxies,
Yeah,
not
that's what I'm saying.
from
Like it's
Earth.
like our perspective. Oh yeah, but that's what I'm saying. It's like, oh, you're asking what size of the galaxies? Is that what you're asking?
I am asking in a low mass galaxy there are all many stars, and is the stars that are is the stars closer than the in compared to the high mass galaxies? Is
No,
the stars are
closer to
farther
what? Like closer to each
closer, like
other, or
if in a galaxy, like we have star A and star B, and in
yeah.
a low mass galaxy, and same at a high mass galaxy, that distance between that star and star B is less than enough high mass galaxies, or that
Okay,
is
okay.
greater than, or is there
Yeah,
anything?
that depends on the type of galaxy. So there are like if you have like a normal galaxy, so it entirely depends on the type of galaxy. It's like if you're saying the size of the galaxy is compact, then the stars are like maybe closer to each other. But then you have like ultra. There's something called as UDGs or ultra diffuse galaxies, where basically it's very high mass galaxies, but the stars like it's like spread out. So yeah, it entirely depends on the type of galaxy and how it is formed. It does not depend on whether it's low mass or high mass. Does that answer your question, Akash?
Yes, Di. Thank you, Di. I got the answer.
Okay, so the next question I'll go to is Ayan's question. So Ayan is asking if there is formation of black holes from galaxies and vice versa, then the energy, if transferred, then is the energy transferred between them? So why is it called that law of conservation of energy is violated in case of black holes?
Oh, because it's conservation of mass energy and not just conservation of energy, right? Because mass is being because matter is being like, accreted onto the black hole, which is producing the energy. So Einstein's theory is working here. It's like E is equal to mc square. So m is being like mass is being converted into energy. So it's conservation of mass energy and not just conservation of energy.
And Akash has made one last question. And after that, I guess Aritra has a question of sorts. So I'll ask this after this one. So Akash is asking, is there any quantum phenomenon occurring during black hole formation at the quantum level? So he's asking, conservation of energy may not be followed.
So there must be some quantum phenomenon happening at black hole formation. Yeah, there must be. I just don't know about it. Yeah, I stay away from black holes, specifically black holes. But yeah.
Okay, actually, then Aritra was asking, there is a myth that white holes exists, but is it that according to Einstein, this is not correct?
I have not heard about white holes at all, so I don't know anything about it.
Okay, Didi. So these are all the questions from the chat box, and so I guess if anyone else wants to ask any other questions, you can always turn on your audio and ask.
Yeah. There is a video that I wanted to share if you guys are
Yeah, sure,
okay.
Didi.
Like there's like
Sure, Didi.
2000, like last year's Nobel Prize. Let's see. Okay. So this is actually pretty amazing. So this is the video which is mind blowing. So this is how Andrea Ghez actually found the black hole at the center of Milky Way. Wait, let's see, how do I do that? Okay. These are stars. Like, do you see the star here?
Yes, Didi.
Yeah. So Andrea Ghez just spent 20 years only focusing on that star. This is called as an S2 star. And she spent 20 years tracking its orbit. And based on that, based on just that one star for 20 years, she found that Milky Way has a central black hole and she measured its mass. So I think it's pretty amazing. Yeah.
Okay.
Any other questions?
So does anyone else have any other questions?
Hello,
हाँ
hello, Didi.
Yes.
Can you hear me?
हाँ पूछो. Yeah, I can hear you.
Based on only one data from only one star, was it enough to predict the center black hole of our Milky Way?
So that was the star that she started with, but there were like many other stars as well. But that was the star that was closest to the black hole.
Okay. Okay. Thank you.
Any other questions? If not, then I guess I can stop the recording here. Okay.